Okay, so now, without any further ado, it is my privilege to introduce our keynote speaker, Andrew Moore. He is the Dean of the School of Computer Science at Carnegie Mellon University. His background is in statistical machine learning, artificial intelligence, robotics, and statistical computation for large volumes of data. He joined the CMU faculty in 1993, and in 2005, he was elected a fellow to the American Association for Artificial Intelligence. His research group has devised several new ways of performing large statistical operations efficiently, and in several cases, accelerating the state of the art by several magnitudes. In 2006, Dr. Moore joined Google as the vice president, where he was responsible for building Google Pittsburgh, a place where you wouldn't necessarily think Google was excited about stuff, for CMU is there, and they had Andrew to start it, so how great. There he worked on many components of Google's advertising and e-commerce. Other major systems developed at Google Pittsburgh include detection and prevention of fraud using human-assisted active learning, advanced crawling algorithms, automatic detection and diagnosis of emerging problems in massively scaled software services, predictive optimization of display campaigns, along with many other things. He returned to CMU in 2014 to become the Dean of the School of Computer Science. He's been a contributor in our field in education, research, and development for a long period of time. And my first interaction with some of his work was a data mining tutorial that he had posted on his website that has now been downloaded by over 1 million people. So obviously a great tutorial. Please help me welcome Andrew Moore.
Well, thank you very much for that introduction, and I am really excited to be here today. This is a very good day for me. I wanted to first really thank National Science Foundation for all the funding over the years. And it's interesting to me that in 1999, NSF actually completely boosted my opportunities and the opportunities for my graduate students with 2 large grants, one in, I think it was an ITR for astrostatistics and using algorithms for doing very large-scale cosmology data, and at the same time support for getting into biosurveillance and detection of disease outbreaks. And the reason I was just thinking about this as we had our earlier discussions, I look at the students who were involved back then in the early 2000s in doing this stuff, and they have all gone on to really revolutionize aspects within large companies and within industry, and in some cases in the security world of data mining. And it is, to my mind, a perfect example of what the National Science Foundation does. One of my students, Ting Lu, who was funded under this, came across some methods for doing very fast nearest neighbor searches on images, which is now built into Google Image Search and has been adopted and massaged for a whole bunch of other ways. She is now in a position where she's making policy decisions around, in this case, advertising, which is actually having an impact on the economies of countries that are working with this stuff. So it's a very clear success story for me of how the early investments in large-scale algorithms really paid off. And I could see several friends from academia. Lise Guitor is down there, who've had similar patterns thanks to this sort of early funding that happened. What I wanted to do with this talk, one of the things that for me personally right now is very, very interesting, is I moved from my academic role to Google and got pretty much obsessed with Google. I ran the computational parts of the machine learning parts of the advertising system for a while, and also then built the areas around e-commerce and shopping. And that was extremely interesting. And what I want to do is talk to you a little bit about some of the computational and policy issues that we faced within Google while doing this. here's the interesting thing. I don't feel proud of this, but at that point, my brain was kind of split off from what the rest of the world was doing. And this is a problem in large companies like Google. You start to do your own parallel evolution. And during that period of time, we did some amazing things, and we missed the boat on some things. So what's happened to me is 4 months ago, I came out of Google into the world, and I actually started reading about things like the Big Data Initiative and other things going on. And it was really interesting for me. It was a little bit like what I imagine it might be when we meet aliens for the first time, and you start to look, oh yeah, you guys did it that way, you guys did this way, yes, you're right, that was a big thing. Ah, that's interesting, we didn't think about it. Or, hey, you guys have completely forgotten this other important thing. So what I was going to do in this talk today is really talk a little bit about some of the contrasts that I had running engineering groups dealing with very large data rates and large amounts of data, and what I'm seeing now that I'm coming out and I'm responsible for setting up a data science strategy within a university. So that's what I'd like to do. I want to comment that I extraordinarily welcome questions or comments or observations while I'm talking. I'd be much more comfortable if this was more like a dialogue. And this goes for everyone in the room, not just the people with the participant badges. So I will sort of consider it a metric of success of this talk if I'm interrupted about 6 times. And then the number of times away from 6 is a reduction. If I'm interrupted every minute, then I've probably not been clear enough. All right, so please do bug me. Okay.
You know that there will be microphones also after he speaks, so if there's a question you want to hold off on, feel free as well.
Very good, thank you. So let's get started. What I'm going to do is break this talk into two sections and try to do them fairly coherently with some specific examples. I'm going to talk about some of the large data systems that I had to deal with in Google. It's not that this technology that I was dealing with is particularly special, but it is in many ways different. So I want to try to express some of the differences. Then what I'm going to do, just because of the way that Lisa described the goals of the workshop, I decided it would be fun to give you my completely personal, off-the-cuff opinions as to the 5 recommendations I would have for pushing forward in the world of very large data. And you can take them or leave them, but I hope they'll be interesting at least. So let me talk now about life in a large search engine company. The bigness of the big data is pretty substantial there. Not always, but in many cases it is. So I'm going to give you a query which is running on some search engine. I'm not going to tell you which search engine. All I'm going to tell you, if you look on the top left-hand corner, the last letter in the name of that search engine is an E. So what happens when you type in something like digital pen on the search engine? Of course, you get a bunch of results. And if you look, you see a 0.69 seconds latency report. Actually, less than 100 milliseconds are within the data center. Most of that is network in and network out. So we have a budget of less than, for most parts of the page. Some of the page we're obviously rendering even after we've started to display other bits. For most part of the page, we have a budget of less than 100 milliseconds for giving an answer. And during that time, we need to match this query against all the possible useful forms of answer that we could give. So I'm going to talk about some of the biggest interesting components of this. So before we even talk about what happens at serving time, I want to talk about what's happening in the background all the time. Because this is where I probably had more than 2/3 of my entire efforts going into this. Because it's really tough. So we have Google has unstructured facts coming into the system. For this particular system, which is around advertising and e-commerce, the facts that were coming in were partly from scraping many data feeds provided by different kinds of commercial entities, some anti-fraud agencies, and many other things like this. The peak rate of ingestion was in the order of between 100,000 and 200,000 facts coming in every second. And these are actually quite large chunks of data. So it's extraordinarily interesting just to get the system scaled up the architectural level so that you can get this data into storage of any kind. And it really is almost the desperate race just to get it stored somewhere so that you can start to then massage what you're doing with the data. That question of dealing with very, very large ingestion, I think, is relevant more generally. It is not just a search engine specific problem. I'll talk a little bit more about that. But of course, while this stuff was coming in, and remembering it's always coming in, so there's no notion of a batch job, we have to build this second box here of decorated entities which are referred to in the facts that are coming in. So the decorated entities reflect the fact that in the last few years in search engine world, and more generally across commercial internet companies, there's been a huge movement away from thinking about indexing and retrieving documents to indexing and retrieving entities. And so it's not good enough now if someone asks a question like, I got a funny, remove smell in basement. That's a good question. In the old days, a search engine would look for documents which mapped maybe with some synonyms, the substring remove smell in basement. These days, all the search engines, including Amazon, but certainly Microsoft, Apple's Siri, and Google, have to understand that that's related possibly to things like dehumidifiers and being ready to serve results which could be useful for that. So it's no longer a document matching problem. So in order for it to not be a document matching problem, you have to have a store of something else. And for us and many other places, it is the store of entities. And getting from the crappy facts to the decorated entities is really important, and it's very, very computationally interesting at these large data rates. What I like about this is this matches what many people were writing in grant proposals in the late 90s and early 2000s, all about going from data to knowledge. This is really happening at the moment. It's just really painful to do it, and you would be horrified when you saw all the scotch tape we have in place, Google has in place, to actually do that, especially to keep it running in a streaming fashion, which I'll talk about later. So there's other things which I put a lot of effort into. Firstly, images are coming in at this same kind of rate. And a good example of the kind of images I'm talking about are images of products for sale. Again, no one would show anything related to e-commerce these days without there being some imagery related to it. It's very useful for the users. It gives a confirmation that it's what you're looking for, and it's more pleasing. It's more what you would want if you're talking to your personal concierge and asking them to tell you answers. Both the images and the unstructured facts. Part of the turning them into decorated entities is, of course, this normalization problem. If I'm referring to the Logitech IO digital pen in one place, and somewhere else I'm referring to a mention of the form, the fourth digital pen created by Logitech in 2012, and all of these mentions. Someone's got to come through and actually decide which are referring to the same thing, and ideally maintain a probability distribution on mentions as to what the canonical thing is they're referring to. This I mentioned that getting these decorated entities happy was a large part of what we did. A large sub-part of that was just this canonicalization question. Here's something else which is very interesting I'd not encountered before I went to Google, but now I believe it is extremely important. We were running these, we had to run these at the level of, those of you familiar with the concepts of precision and recall, 99.9% precision. Most of the machine learning algorithms and statistical methods I'd used before were much less precise. Just to be clear what it means to have high precision, it means that if I say something is the AJ42 Black & Decker drill, I need to be right. I need to be wrong only 1 time out of 1,000. It's not quite so serious if I just say, I don't know what this thing is, and don't serve it as a result. But if you search for a red dress, or a red Empire waist dress, and you look at all the images, and one of them is a toaster, you get offended. What really offends you, though, and this is really interesting, what really offends you is any kind of compositional query, like what is the cheapest Empire red dress, or where can I buy an Empire red dress near me? As soon as you've polluted it with these bad decorated entities or bad matches, the joins, database joins that you're doing in order to answer the query, those errors compound quickly. And so you end up with a great deal of garbage when you're finally doing your actions. For this reason, unlike in my academic days, Google, and especially Google around retail advertising, geodata, and some other data sources, does have a huge number of humans in the loop, and there are very few systems for background data which run autonomously, and the major companies have invested in large numbers of operations people, very large numbers in some cases. For some applications in the industry, I'm not saying whether this is Google, there are shops of tens of thousands of people, often in Southeast Asia, who actually make a pretty decent living doing the final stages of checking for what these systems are producing. That's very important then, that the systems which are doing the kind of matches that you need in normalization are able to estimate where they're making their mistakes, show those to these humans, and get answers and incorporate them quickly so they don't keep showing the humans the same form of mistakes. That is one of the really big areas, and in fact, when I come to my top 5, spoiler alert, that the human in the loop part is one of them. So I've talked a little bit about what goes on in the background. I want to also talk about what happens at serving time. When a query comes in, and you've got these 100 milliseconds to give not just a single result, but sort of generate a whole page on the fly of information. So you move from a query to a results page. You don't move there directly, and you don't spend a whole lot of time or compute really figuring out what you need to do. Abstractly, what you do is you iterate over all possible results pages and say, for this result page, how happy will the user be if I show them this to them, given their query, and maybe given their location, maybe given their ads profile. And of course, you can't actually iterate over all possible results pages, so there are all kinds of interesting optimizations, even for one little block, one advertisement or one snippet of information. You're still, Google in 2012 told the world publicly that it's got more than 1 trillion objects or entities or web pages which it can match again. So you've got, for each individual component, you've got to find the argmax over those trillion objects. As you can imagine, at that point, you end up writing systems which do incredibly aggressive pruning of possibilities, and then slightly less aggressive pruning, and then eventually end up with candidate pools, I can't tell you how large, where you're actually applying sort of big machine learning inference on it. One of the most interesting parts of this then is you have to have this model sitting there in the middle so that your query can be massaged with the model in order, over the space of, let's say, maybe millions of possible candidate results, to predict the happiness of the user for seeing that model. This model itself needs to be very up to date. What typically happens, and this is not just for search engines, it also includes other parts of e-commerce and the travel industry and the financial industry, world events, or even things like the local weather, local holidays, suddenly local time of day of when a query is produced does actually elicit different reactions from users to different results. So the machine learning model itself, it's well understood that that needs to be as up-to-date as possible. You can't like learn a model in 2014 and expect it to work in 2015. In fact, you're pretty occasionally, if you have a stale model emergency and you're predicting using yesterday's data usually you're using data from the last 9 months or so, but if you're ignoring yesterday's in your model, you give noticeably worse predictions and noticeably less user happiness. So the interesting task that we're faced there is very much the machine learning at a very large scale where you've got to keep your system up to date. So again, all algorithms based on let's start from nothing, build up some matrices, and do stuff in batch are out of the question. I'm going to move along a little faster now. I just want to mention that as many of you are aware, and as we talked about earlier, if you look at the fleet of servers which are running these things, firstly, in order to deal with the scaling, you do have to scale the servers in a very large, aggressive fashion. The latest estimates in the public domain of how many servers Google has ranges from, I think, 1 to 3 million, and the estimates for the number of cores on each server range from 1 to 30. If you look at that kind of scale of number, you realize that you're getting server deaths every few seconds, given the life of a typical piece of hardware. So you say you have to build a layer, an algorithm layer on top of this, which can abstract away and mean that the software running higher up, the machine learning software, doesn't notice that some of the things are flaky. And you can do this with various forms of redundancy and kind of RAID-like tricks with data in RAM in order to help yourself. But, and we and many folks have discovered this, and I was having a great I overheard a good conversation about this with Randy just now. If you make that abstraction too nice, as in you really hide the problems below the reliability layer from the algorithms above, you can lose quite a lot of compute power. So instead, usually when you're running these very large machine learning models on very large numbers of servers, you want to invent machine learning algorithms which are actually tolerant to deaths of servers underneath them, rather than implementing a machine learning algorithm which assumes that all the data is going to be safe and all the parameters that you're estimating are safe, and then relies on a layer of abstraction to actually maintain that promise. That costs, many data centers if you only use that inefficiency, and that costs billions of dollars. So that's a very interesting thing. While you're doing this, you have to know if you've got, I'm going to say this in a nice way, diseases spreading throughout your data centers. If you've got certain classes of servers which are getting sick, or some servers are having a problem which is increasing, say, their network traffic and actually starting to damage other classes of servers, usually you need to be able to diagnose what's going on. And it's very much like an epidemiological investigation as opposed to GDB, for example. I want to mention that another large part of all of this work is to do with trust, fraud, and opinions. And this one, I believe, is extremely important for the national agenda. It's not always desperately important for certain kinds of scientific data that are running purely as a scientific endeavor. But as soon as we have humans in the loop, regular users or organizations which we don't actually know exactly who they are, this is really difficult. So you'll notice, of course, on many results, you've got stars, which most folks understand to be something to do with the general view in the world of how good that thing is. This is a big semi-unsolved problem that everyone, including Amazon, are facing at the moment. Understanding, trying to get a notion of reliability and trust from opinions expressed on the web is so exciting because it's a way of scaling the rest of internet search and question answering without having to do huge amounts of hard work. If what you want to do is to be able to say, okay, Siri, what's the best toaster I should buy? And have Siri, like a friend or a concierge, actually tell you something. But unlike the other things we've talked about so far, that word best is a very different class of computation to answer. One thing that Siri could do is just look at all the stars for all number of stars reported all over the web for toasters. But guess what? That's actually not going to give a very good answer. So this is very important, not just in e-commerce, because if you have a question like, I have a rash, or my friend has been diagnosed with stage 2 liver cancer, you do not want to start giving advice which has been spammily voted up in some ways. While at Google, where the resources are very large, even relative to the National Science Foundation, when it came to trusting businesses and organizations, it was economically practical to just buy 1 million things a year, see if they arrived on time, check that they're okay, donate them to charity if they're not successful. Actually try calling the 1-800 numbers of all the people who are advertising or giving you information, not all the people, a sample of the people who are advertising services on the web, and you can start to operate that way. That becomes very human intensive, and quickly you discover that you're having to build fairly sophisticated statistical models, not the simple large logistic regression type models that you might see in the middle of this diagram, but actual models which deal with the fact that there's maybe a 0.1% of all the data has been checked by some expensive human operations, and the rest of the data, there are some opinions expressed on the web. You need to fill in the missing values to start to figure out which opinion makers are reliable and which ones are not reliable, and start to iterate that to help you decide where further to seek trust. Because a large number of queries or things people need to know do involve value judgments like best. It's an extremely common word to see in web streams. What's the best app? What's the best PDF viewer? And other things like that. Can you advise me on which doctor to see? I feel sick. I'm at SFO Airport. What should I do? Those kinds of queries, they do involve some value judgment. There's a lot of work in order to be able to trust what's going on. Yes, in fact, the question was, do we do any work in presenting the evidence to the consumers? That is a really good question. Yes, in fact, I think this was launched after I left, but now for businesses with e-commerce, when you look at the stars, you can see certification levels of this is a Google trusted store, and that trust is actually based on having done analysis all the way along, and you see a breakdown as to the objective measures of trust. So that's actually one of the critical parts of all of this. If it's just a general measure, you don't know what to use. If it is a measure which says something like, this company says it has 5-day delivery, and we checked, we are confident that 95% of its deliveries come within 5 days. Those kinds of things, you can do that. But as you can imagine, it's extraordinarily expensive to actually do all that testing all the time, so you have to allocate your testing resources very carefully. Good question. Any other questions before I move on? Nope, that's not a question. That's a video recorder update. Here's something that's fun. Without actually knowing it, of course, we really did have this data to knowledge to action mode in the way we're building stuff. So when I saw in the Big Data Initiative that it was being organized this way, I was ecstatic. I really do see this, and you can see it in the architecture of the systems we were building, that This is very much the way, and you actually start to see design patterns and sort of machine learning software design patterns which are working with that. So now we come to the fun bit. How long do I have? 5 minutes? All right, 1 minute per recommendation. These are meant to be fun, and of course, I don't want to be pompous in this, so don't treat this as a strictly academic part of the talk. You're welcome to push back. But these are my gut reactions when I look at what's going on nationally outside the internet companies in managing extremely large amounts of data, and the things which I am very excited about, and some of the things which the faculty at Carnegie Mellon across the statistics department and the computer science school and the College of Engineering and the humanities for policy, we're all sort of buzzing about in order to sort of generate our next 5-year strategy around exploiting information. Here they are. 5. Okay, this looked really clever when I created the slide. Okay. Edible underwear. We have 600 people in Google Pittsburgh, and you hear yowls of complaints when things like this come up. Not for the reason that you would imagine. The idea obviously is pretty horrific. But the reason that these cause so much trouble, as do costumes for your pets, is we are stuffed full of ontologists and linguists who are working on big, quite complex workflows to do with categorizing and taxonomyifying all the entities that are there. They need to categorize and taxonomify not only because it's useful to the users to be able to search for, say, clothes, then maybe women's clothes, then women's shirts, and be able to do those kinds of things. It actually is the underpinning of any strong entity-based system, is you need to have an overall ontology and hierarchical system on top of it. These were things where we had a wall of shame of entities out in the world which defined any reasonable position in a taxonomy. Are edible underwear, does that go under food or under clothes? And of course you could say, hey, it doesn't have to be a hierarchy, it could be a DAG. But as soon as you do that, you actually hit some computational complexity problems. Here's the interesting part about it all. The punchline of it is many humans are involved in large amounts of data, and you should not regard management of really large amounts of data as classic information technology, where we're really taking people out of it. There's a big industry, up and coming, already in place in some places, to do with maximizing the usefulness of humans to help our massive but stupid computers get a long way towards this very, very high precision you need for the kind of services that large data is going to be giving to the world in the future. Yeah,
so
question.
Is some of this done using CAPTCHA type technology, or my question was, some of this categorization, do you really need experts, linguists to do it, or can you do it using like CAPTCHA type thing? Where
it's a great question. So one of the things which we and other places have built is we have a hierarchy, and we actually have a system architecture for the expertise of folks involved in this. So you will see professional linguists and ontologists at the top level, and data modelers as well. They're usually working with teams of professional people with degrees on running particular areas of it. Below that, you have semi-skilled folks who are doing some actual labeling, which can range from things like in a movie, clicking on all the objects for sale in that scene in the movie. And to do that bottom layer, there's different economic models, and in some applications, either the Amazon Turk kind of approach or the recapture approach can be practical. I don't know if this is a good thing or a bad thing. The cost of human attention in the developing world is still very much out of balance with how it is in the United States. And so all these things, we talk about it in terms of this is half a cent a label, this is 3 cents a label, and you can actually then start to look at, if we do Amazon Turk and we know that this is going to be the error rate or the bad actor rate in labeling it, we compare that against the hiring services or building the equivalent of a data center versus using, sort of putting it inside a reCAPTCHA. That's where it goes. In each of these cases, I think that industry is well ahead of what's going on nationally, with presumably the exception of the security services, which will have similar kinds of operations. Good question. This one, I think I'm probably just not up to date with, and I would love to learn more about this. It's extremely important to break up the roles of what's going on in large-scale data. So much as we have a networking stack, and you typically think of a different level of software components in an operating system, I think it would help us make progress nationally and internationally if a body like this worked very hard to define some kind of layers of a data science stack. That will help a lot in setting up education programs. It will also help a lot in understanding what kind of skills are needed for particular deployments. I actually do not think it's practical anymore to use the heuristic of, we'll have someone who comes in to learn about data science who's already got expertise in one level and train them to be an expert in all levels and then send them out to do well in all levels. You need, at least for the very large pieces of data which are just on the border of being possible right now, you need really strong expertise. So I would be delighted, and I'm hoping someone says, be quiet, Andrew, we've already done this, don't worry about it. But if not, I think it's very, very useful for us to work on this problem, especially as even within a place like Carnegie Mellon, this kind of apparatus can help us actually delineate roles and responsibilities for different groups. And of course, it brings us to the dream, which we're very good at CMU, I should say, completely unbiasedly, of someone working at the very large data architecture level, kind of things that Randy has been pushing and is now working very nicely in our PDL. The architectural stuff to do with managing the data at the low level has an API where someone at the middleware layer who's doing machine learning algorithms can then have an API with the folks at the top layer doing the decision support work. And the more quickly we do this, I think you'll see the same kind of speed of innovation accelerating that we saw in networking in the 80s and in other areas of software engineering in the 90s. Next, the architectures which are out there, primarily the web service clouds type architectures, are very, very useful for some embarrassingly parallel stuff, including sort of dot products and selects, and using that in a bunch of algorithms like deep networks or logistic regression or some other kind of graphical model inferences, which primarily have that as their computational complexity. But that is not the only real big metal stuff that we need to do for managing large data. The general area I'm going to call fuzzy joins of being able to actually match with imagery, obviously in the world of tracking and signals with noisy telemetry data, or in the world of documents and user questions and facts being ingested. All of these things need fuzzy joining technology, and the streaming architectures, sort of most famously exploited by the MapReduce and Hadoop type methods, can be used for them, but very inefficiently. And I really am looking for architectures which can support petabyte and exabyte level equivalents of random access and key value stores in order for us all to be able to make progress here. Number two, entities. This one I think has This one has been discussed greatly, and in fact, the concept of the semantic web predates the explosion of our excitement about data. The interesting thing for me is that in the commercial world of search engines and more generally question-answering types of systems, for a while, the whole field got a little distracted by just retrieving documents. And there is something magical about retrieving documents with strings that match your query. You do feel a little bit like the ELIZA AI program, that the system is being pretty smart just from doing that. But we are beyond that now. Most internet companies have publicly stated that they expect browsers to die, or at least the heavy use of browsers by regular consumers to tail off and start to decline. And you can actually see that in public reports at the moment. What's coming up instead are the Siri types of interfaces where people expect with a mobile device to be able to ask questions about stuff. And to answer those questions meaningfully, you need to be able to compose entities. One of the most exciting things which I'm looking for and have heard from colleagues and friends, folks at IBM, folks working in schema.org and Freebase, are the gradual emergence of groups of people actually trying to build data stores of between trillions and quadrillions of entities out there in a way where folks can build businesses and applications which are able to refer to the entities. A really simple example of this is even a humble person doing statistical consulting on their own who's got the equivalent of an Excel spreadsheet or an R script with a small amount of data, perhaps a database with 1 million rows in it, where some of the rows are the free text of locations. I think we should not feel proud of ourselves until it's relatively easy for them to right-click on that and say normalize and have another row appear in the spreadsheet with the exact world-defined locations as to what those things are, because at that point they can then get all the additional secondary information about those locations and things near them, and so forth, as that goes on. Locations is one thing. You can imagine organizations is a huge thing, especially for those new to Washington, D.C. who are not familiar with all our organizations. That is really, really important and hard to deal with. Me right now at CMU, it's master's programs. Our bloody master's programs are all over the place. There's not even a clear data model for those, and there's only about 60 of those. People, diseases, genes, each of these things, the extent to which we have a single worldwide consortium which lets you do this join, and suddenly we find that all our data scientists around the world who have been struggling are able to do compositional stuff. I think that will increase the IQ of our data people and be a huge win for everyone. Number one, finally, is the top of the stack. And this, I think, is my most pathetic thing, even though it's top of my list. The reason it's my most pathetic is it's very clear we're already all in agreement in this. You see this in the emphasis of action in the concept of data to knowledge to action. For me, and some of the things we're doing at Carnegie Mellon, we break this action part into two fairly distinct parts. The autonomy, the fact is that we need all this data to build models to help intelligent systems take care of themselves. These are data centers, distribution centers, military logistics centers, obviously many kinds of robots, many kinds of smart buildings. They need to be autonomous, and so they're the folks, they're the applications that need us to process the big data into a useful model. Having an emphasis on big data infrastructure has now been set in place quite nicely in sort of the national agenda. I really hope we can push to exploit it. And what I fear is that without absolutely pouring as much energy into the disciplines of autonomy and cognitive assistance, large data will turn into a sort of catchphrase for general ad hoc data browsing, data visualization, which is much less satisfactory and much less useful than big data analysis, which is directed towards a specific task. I break up into autonomy, which I've mentioned, and cognitive assistance, which I haven't. Cognitive assistance is the use of large data to make people smarter. And it very much includes Joaquin Phoenix in the film Her having a little thing in his ear telling him what to do. That is, I would be really, really surprised if we're not all doing that ourselves within 2 or 3 years. There's so much push towards this ability to have a cognitive assistant help you, not just in order to tell you which part of the shopping mall to walk to buy your clothes, but to remind you if you're a biochemist working with a particular protein that one of your reagents is something which someone across the world recently discovered had an unstable condition in some situation. That is what I really would like us to do, is be using the power of big data to make machines more autonomous and to make humans essentially have a higher IQ. And that's what really inspires me about what's going to happen next. And that's it. Question?
Wait for someone with a microphone.
For giving us a little view behind the curtain. It's always fascinating to hear what's going on at Google. We don't often hear enough about that. The comment is just quickly about the stack. One thing that has happened in the software stack that's different than what happened in the networking world is that there's a huge open source community that's been developing all sorts of software for big data. And there is an architecture that's been developed in sort of a bottom-up grassroots way. And so I just wanted to point that out because it's not clear that we need sort of a top-down, standardizations effort right now to make that happen, because it's sort of happening organically, inspired by things that happen at Google and other places. The question is one that I've been facing. You mentioned that Google has somewhere between, according to your calculations, 1 million and 90 million cores, I think, if I did my math right. And the question I have is, there aren't many places in the world that run at that scale. And so I worry about coming up with solutions for problems at that scale. Will those solutions be the right solutions for the vast majority of people that are dealing with data? And if by focusing on those sort of outsized problems, will we miss kind of some important solutions that would help many more people?
Those are both excellent points. The first point, I agree, and I think it would make far more sense for us to be building this around some of the open source abstractions. Second point, I actually have a very strong feeling about. First, as you go from brain science to other aspects of biology to some of the work in security, there's a really strong group at CMU working, funded by DARPA, on anti-sex trafficking and so forth. You do start to hit these volumes of data. What's rare is for you to have to worry about the serving scaling of being able to answer 1 million queries a second. So that, you're right, might be over-engineered. The other part, the scale of the data, I'm actually really interested to see that it's at the trillions of event level is something which I'm seeing in a bunch of different disciplines. Certainly the disciplines that I'm most familiar with, but in some of the other ones. Here's what's interesting. And is anyone else here from Google? Because they probably won't like this. We did get fat and lazy at Google as computer scientists. There's one particular thing which I alluded to, which I really feel passionate about, to do with these fuzzy joins. You can imagine, if you've got to do a fuzzy join of, say, 100 million pieces of free text with another 100 million pieces of free text, you could come up with a great algorithm which does some n log n kind of tricks to actually do that matching very efficiently. Or if you happen to have somewhere between 1 and 100 million cores, you could just run each of them as a query tractably and basically linearize or some extent quadratize your algorithm. That's somewhat of the problem with being too rich with compute. Since I've come back to CMU, there's some work going on there by Alex Schmoller and Eric Jing, which frankly embarrasses me, because not having that level of compute power means that they can means that they have got stuff which is, in my opinion, in some domains, almost as good for 3 orders of magnitude less hardware involved. So I do want us to try to get to this Google scale, but I do think that it needs computer science, algorithms, systems architecture design development by the organizations represented by people in this room for us to be able to have the equivalent of 1,000 Googles. If we had Google's resources on brain, for instance, right now, I believe the whole field of brain research would be moving a factor of 2 or 3 faster. Yeah.
You mentioned that the precision has to be very high for these queries. The false positive has to be very few.
Yep.
You can tolerate a toaster for a query for redress. Can you comment on false negatives? What is it that you are not able to see? Because now with search engines could make somebody completely invisible if they don't show up.
That's a really, really good point. So I will concede happily that some of my obsession with the high precision is because of the structure of the problem, where you're showing a huge bunch of results to someone and they are unhappy if they see something stupid. And it really does. You can see studies where throwing something randomly stupid into there actually completely kills the click pattern of folks who are actually doing information-seeking activities. But the big question is, what we really want. When we talk about high precision more generally, you can think of say a cancer specialist researcher who's got a bunch of different drugs and needs to match them against some of the places historically where they've worked out well. It would really slow them down and actually take them down to a blind alley if we had normalized some of that information. So, and then if they actually ask a 2-step composed query, then it could really make it disastrous, and they will learn not to try to use these kinds of systems. But unlike the consumer case, where it's not a disaster if you don't actually get shown the Breville X500 toaster, it's extraordinarily bad in some of the other cases if you're told this is not a match. So it doesn't reduce my thesis that we've got to cheat and use humans at a much larger scale than perhaps we've talked about, but I will concede that it's going to be, in many cases, for the false positives and the false negatives. Yes, question.
Do I have the mic? Yes. I'm struck by some of what happens sort of at the grassroots level on up, such as Google and so on, and perhaps elsewhere in the technology industry. And however, my question to you is, what, if anything, would you ask that be done top down so life would be easier for even more innovation?
Entities, very much entities. Google, as you know, is publicly building the knowledge graph on acquired freebase, but I'm not speaking for Google, but my guess is that Google would be very happy if there was a world's shared knowledge graph. And that, I think, has to come, it may bubble up from somewhere like the World Wide Web Consortium bubbled up from some part of the world. But anything we can do to accelerate that and make sure it comes out well will help. One of the dangers here is data silos, where, for example, let's take Amazon's investment in understanding everything for sale in the world. That piece of that database is worth a vast amounts to Amazon. There's no way it would make any sense for them to share that publicly with the rest of the world. That I can tolerate, especially as it gets to the levels of really fine-grained information about every product, which is like a commercially advantageous thing for Amazon to work on. What would be a shame, though, is if these kind of walled-gardened approaches happened all throughout the industry on things which people actually need in their daily lives, policymakers need, so that no one could compose queries. Much of the same way as the false positive and false negative. I do not want to see lots of barriers between these sources of data. It should not be the case that in order to... So let me back up a bit. I'm going to answer, if I'm going to write an app which is helping people manage their diets properly, it turns out that app does need to know that the Burj Khalifa is in Dubai. It may sound crazy, but as you start to compose extra evidence about things that you're going to answer, the entities that you're using in these queries quickly escalate, and not every app maker can license all of this data. If there is something perhaps with perhaps like 10 to the 3 to 10 to the times 6 times more entities than Wikipedia and strong information, then I think you're going to see a very quick growth in innovation around apps which make use of all the data that's going on. You'll also see individual data scientists, probably some people in this room, and certainly people who work for people in this room, being much more productive when with their own data it is a small issue to get secondary information about the entities and events that are involved in this. I do believe that this sits there with some of the ISO standards and some of the WWW consortium standards as another thing which we urgently need standards around. So if there's one thing, that's the one.
I know there's a lot of other questions in the room, but we have a busy day ahead of us, and we're going to have a lot of opportunity to talk to Andrew the rest of the afternoon and the rest of the day, too. Please thank Andrew once again.
Thank you. Thank you.